In this video, we're going to prove the following fact. The quadratic congruence x squared plus 1 is congruent to 0 mod p, where p is prime, only has or does have a solution if and only if p is congruent to 1 mod 4. Okay. Proof. Let A be your solution. So we're going in the forward direction. It does have a solution. Let A be a solution to x squared plus 1 is congruent to 0 mod p. That is, a squared plus 1 is congruent to 0 mod p. Now, p does not divide a. I claim p does not divide a. If p did divide a, that would imply that a squared plus 1 mod p will equal to 0 plus 1 mod p, which will be congruent to 0 plus 1 is 1 mod p. But we want it to equal to 0 mod p, and it doesn't. So p must not divide a. So p does not divide a. And p is prime, and p doesn't divide a. By Wilson's theorem, a to the p minus 1 is congruent to 1 mod p. Okay. Now, let us just look at this from a different point of view. A to the p minus 1. I would love to have a squared because we're talking about a squared. Well, if I double the base, if I double the power, I have to half the power. Now, a squared is negative 1 to the p minus 1 over 2 mod p. Now, there are four cases in theory that p can be. P can be 4k, p can be 4k plus 1, p can be 4k plus 2, or p can be 4k plus 3. But no. P can't be a multiple of 4, because then p would be 4 times an integer, and p's prime. Down here, we have p is 2 times an integer. So, product of 2 integers can't be. So we're left with that p can only be one of those two. And maybe it can't be one or both of them. But so far, we knocked out 2 of them for sure. Okay, so the question is, can p be of the form 4k plus 3? That's what we want to see. Either it can or it can't. If we run into trouble, then guess what? It can't. Okay. So now, we're just going to build up on this. We have a to the p minus 1 is equal to a squared raised to the p minus 1 over 2, which is equal to negative 1 to the p. 4k plus 3 minus 1 over 2 mod p. And this is equal to, or congruent to, well, this numerator becomes 4k plus 2, which is 2 times k plus 1. And when you divide it by 2, you just get k plus 1. You get 2 times 2 to the k plus 1. But somewhere we said this as well. This is congruent to 1 mod p. Okay, so this being an odd power, this is gonna become, that's gonna become negative 1 mod p. So what we have is this is equal to this. Well, that implies that p must divide their difference. 1 minus negative 1. That is, p divides 2. Well, this implies that p is even. And p is odd. Even plus odd is odd. And is odd. Well, that's a contradiction. P cannot be even and p cannot be odd at the same time. So, can p equal this? No. Okay. Therefore, then p is equal to 4k plus 1. But this is what we wanted to show. This says that 1, let's see how they worded it. This says that p is congruent to 1 mod 4. But that's exactly what we wanted to show. Now we need to go in the other direction. Now we get to assume that p is congruent to 1 mod 4, and we want to show that ax is congruent to x squared plus 1 is congruent to 0 mod p. Let's just have that up here. So we have it congruent to 0 mod p. That's what we would just love to show. Congruent to 0 mod p. Okay, so what we have is the following. Let us look at p minus 1 factorial. This is equal to 1 times 2 times 3 all the way up to p minus 1. But you know what? I want to say hello in the middle. You're going to have two middle numbers. One middle number, I'm sorry, that should be times. One middle number would be p minus 1 over 2. 1 times 2 times 3 all up to p minus 1 over 2. Let's even bracket that up. And the next set will be p plus 1 over 2. And then all the way down to p minus 1. Now, let us look more carefully at the second set of brackets. We have p plus 1 over 2. Well, if I add p to it, then we have, so this is really negative p plus 1 over 2. And if I add p to it, the mod won't change. That p becomes 2p, so I can put everything over p. 2p minus p is p. Let's not forget to take away the 1. So this here, this is congruent to that. But I can put the negative on the other side. This is the same as negative p minus 1 over 2. The next term here will be p plus 3 over 2. Okay, if I look at negative p plus 3 over 2, that will be p minus p plus 3 over 2. The p's like 0. So once again, we have 2p minus p plus 3 over 2. 2p minus p is p. Let's not forget to take away the 3 over the 2. Every term in here matches up with the term in here. The first one here, and this one matches up. The second one in from the right, the second one in. The third one going from the left, the third one from the right. The fourth one, the fourth one. They're all negative of one another. They're all going to be negative of one another. So, what this product really turns out to be is we have 1 times this one. If you have p minus 1 and you take away p, what you're allowed to do is negative 1. It's the negative of that one. The one right before is p minus 2. Well, you know what? Let's just take away the p. You get negative 2. So you have 1 times negative 1. The 1 comes from here. Sorry, it comes from here. The negative 1 from there. The 2 comes from here. The negative 2 is the second one in. The 3 from here. And then a negative 3. All the way down to p minus 1 over 2 and negative p minus 1 over 2. Okay, so we have 1 minus sign, 2 minus signs. You're kidding me, they're counting for us. 3 minus signs. We have negative p minus 1 over 2 negative signs. So that's going to be negative 1 to the p minus 1 over 2 times, well, whatever I'm about to say, it's going to be squared. We have 1 times 2 times 3 all the way up to p minus 1 over 2 factorial. But we have it again, 1 times 2 times 3. I already dealt with the negatives all the way up to that. So this becomes squared. Now, okay. So it becomes negative 1 to the, remember, p was 2k plus 1 minus 1 over 2 times p minus 1 over 2 factorial all squared. And this power, the 1 minus 1's cancel out. You get 2k over k, 2k over 2. Sorry, I apologize. It was 4k plus 1. The 1's cancel. 4k over 2 is 2k. It's an even number. Negative 1 to an even number is 1 times this over 2 squared. Well, this is equal to p minus, this is congruent to p minus 1 over 2 factorial. Actually, the whole thing is factorial. All squared. Now we're going to invoke, oh, this is modulo P. Right here, we're going to invoke Wilson's theorem. This is -1 mod P. This is congruent to -1 mod P. So, combining all this, we have -1 is congruent to something squared. No, let me just say it slightly better. This is the same as P minus 1 over 2 factorial squared is equal to this, congruent to -1 mod P. One more line. I'm going to bring the 1 to the other side. So, squared. So we found that when I square this, when I square that, and I add 1, I get 0 mod P. So I think earlier I called the solution A. So the solution A is, well, actually, the name of their unknown was X. So X is equal to P minus 1 over 2 factorial all squared. That completes this proof. We found out if P is congruent to 1 mod 4, then the solution to something squared plus 1 is congruent to 0 mod P. Well, that something is P minus 1 over 2 factorial. Actually, I don't need the square for X, because the problem said X squared is congruent, X squared plus 1 is congruent to 0 mod P. We're just to find out what X is. And there it is. Use that for X. If you like videos like this, subscribe to my channel. Click the like button. Tell your friends about my channels. Tell your enemies about my channels. Leave a comment. See you guys in the next video. Watch and learn.